Now, I do actually have one more homework assignment for you guys. And it's going to be brief. It's going to be unlike all the other ones that we've done this entire semester. Because after today, you will have learned and gone over all of the math needed for the test, the exam. Since I'm going to be collecting your homework this week today, my goal is we finish it today, I take it today, and I grade it for you over the weekend. And since we won't see each other until a week from today, I wanted to give you at least something to have a little bit of physics work that you can be doing in that time to help keep moving your mind towards the physics you'll be doing in the next couple of classes. So before you go today, there is a homework aid, but it is unlike all the others in that it is a very short, numbers light assignment. And I do encourage you to work on it together. This is simply, and it's titled as such, an investigation of Newton's laws. Because Newton's laws is, as much as what we've been doing so far is basic foundational physics, this is the core of basic foundational physics. So I wanted you guys to at least be exposed to this before the semester ended. So this is, I feel, a way to be able to start incorporating it. We'll talk more about it later, but to at least start getting it into your heads. And I will be uploading notes that you can use to read through and then interpret for these questions. I encourage you to work together, read those notes. Feel free to Google things as well. The internet is a tool that you can use on your homework. Just to look at and begin thinking about these questions and these concepts. This will not be due next Friday. This will be due later. This is just, I want to go ahead and get it so that you can have it in your minds. Have the laws of motion in your minds. That said, the main thing we need to focus on today is the last three questions and subsequently what they involve: falling and projectile motion. This is sort of going to pull together all of the, at least three of the Fantastic Four formulas and start talking about a specific, it's going to combine displacement, velocity, and acceleration all together, and very specifically it will incorporate the most common type of acceleration that you have been experiencing your entire life, gravity. So let's go ahead and get started so we can wrap up homework 7 together. We all live on planet Earth, and the planet itself is very wonderful for a lot of reasons. It's got, a million factors that make it suitable. The only suitable planet we know of is to sustain human life without any form of terraforming or having to wear a suit. And we were designed and built to operate on Earth's surface where the gravity level is at a specific amount. Now, gravity is a force. We haven't defined force yet, but force is very important. So, this formula right here is the definition of force. Force equals mass times acceleration. Additionally, this will help you on the little brief Newton's assignment at the front of the room. This is not just the definition of force, it's also Newton's second law of motion. So there's one of the three laws right there. This one was very important because any single time a force has ever existed in the universe, it's been pushing on some object with mass, causing that mass to accelerate. When you exert force on something, the thing has to exist, it has to have a mass to be pushing on it in the first place, and when you push on it, it starts moving. It wasn't moving, now it is moving, therefore its velocity changed, therefore it accelerated. So all forces cause accelerations. Every acceleration ever has been caused by a force. Baseball's a good example. The ball's moving towards you, you hit it, it accelerates, and now it's going backwards. And the word definition of force, a push or pull on a mass which causes acceleration. Now, there are times where there will be multiple forces on an object and it ends up not accelerating. For example, any object sitting on the desk isn't accelerating, but there are definitely forces acting on it. We've got gravity pulling down, the table pushing up. So things only accelerate if the forces on it are imbalanced, but by and large, the purpose of a force is to make mass accelerate. I actually learned this from my Taekwondo instructor as a kid, more so than my science teacher, because he would always tell me, force equals mass times acceleration. If you want to punch harder, you either need a bigger fist or you need to punch faster. And I can only control one of those two things manually. So, on Earth, we have gravity. Gravity is a force. That force is pulling down on us constantly. That force of gravity acts on our mass, which causes us to accelerate towards Earth's core. We call this falling. So anytime something falls, it is accelerating towards the ground due to the force of gravity. And conveniently, on Earth's surface, unless there is an extreme exception as to why it might not, every object will accelerate towards the ground at the same rate. Every object, barring the case of flying or a parachute type situation, falls and accelerates towards the ground at the same rate. This one right here, negative 9.8 meters per second squared. The negative simply means down. As you're writing that, one more definition I'm going to put on this side of the board and keep here. Now, when an object is falling and is accelerating at negative 9.8 meters per second squared, we consider it to be in the state of free fall. If something is in free fall, it is only falling and only due to gravity. It is accelerating down at this rate, and there is no other force and no other acceleration involved in that interaction. Now, my handwriting is terrible. Please, if I need to rewrite something or specify what something says, do please let me know. So, when I hold up this marker and I release it, once it's out of my hand, gravity is the only thing pulling on it, so it will fall straight down. Similarly, not immediately obviously, but similarly, if I throw this marker, as soon as it leaves my hand, even though I threw it, it's still falling. It might travel upwards, but it's still falling the whole time. Because once it leaves my hand, it is entirely up to the mercy of gravity. So if you throw something upwards, and as long as it is as long as you threw it, as long as it isn't flying and doesn't have a parachute, if you threw it and it is now entirely under gravity's rule, it is technically falling. Because the entire time, it's accelerating down. So this number will come up all the time. You will never escape it. Now, important thing to note, this happens in the vertical axis. So if I can further specify y direction. Because of the definition of free fall, this comes with a little asterisk. Since you can only be accelerating due to gravity while you're in free fall, that automatically means you have no x acceleration. If you are falling, you cannot be accelerating horizontally. You could still be moving horizontally, but not accelerating horizontally. As an example, there's a lot of famous cases where someone has dropped two objects to prove that they fall at the same rate. I think there was an experiment where Newton dropped like an egg and the equivalent of a bowling ball off of a building, and they both hit the ground at the same time. It's because they're both accelerating at the same rate. Additionally, it doesn't matter the mass of the object, it generally doesn't matter the size of the object, they will fall at the same rate. Similarly, it also doesn't matter if one of them was thrown horizontally, because the horizontal axis has nothing to do with the vertical axis, and because as long as you are falling vertically, there is no horizontal acceleration, the vertical axis is not affected by anything going on in the horizontal axis. So, I'm going to try to have these land on the table. Black marker will be thrown, green marker will be dropped straight down. And ideally, you should hit at the same time. Horizontal movement has nothing to do with the falling itself. You can throw this. The extreme example would probably be a bullet. If you fire it horizontally, it will eventually fall and hit the ground. It's just likely to hit something first. And this motion here, the motion of both objects, we can track the different motion in the x and the different motion in the y for both of them. And even though the yellow ball is constantly drifting further away from where it was dropped, you can tell that they're both still falling at the same rate. You can also tell that as time elapses, they're both getting faster. Up here, there's like a millimeter or maybe a centimeter between each of the frames of time. Down here, there's inches between each frame, each second that passes. That's because when you are falling, you're accelerating. You're getting faster. This is why things tend to hurt more if you fall from higher up. If you jump off of a 1-foot step ladder, you haven't been accelerating long. You won't hit the ground very fast. If you fall off a 10-foot ladder, you have more room to accelerate. You'll hit the ground at a higher speed. It'll hurt more. Good so far? Any questions so far? Okay. Let's start utilizing these principles. I'm going to try to put, yes, the homework up on the screen. Numbers 19 and 20 are very similar to one another. I'm going to show you, each question I try to lay out in steps, I'm going to show you exactly exactly what each step should look like. We're going to do them together. We'll do 19 first, and then we'll compare it to 20. A rock is thrown horizontally from the top of a 30-meter tall cliff. I'm going to skip ahead a little bit. Part A asks us to draw this situation. There's a lot of pictures in physics. It's good to draw them. Let's do that one together. We have a cliff, 30 meters tall. We have a rock, and we throw it horizontally away from the edge of this cliff. So just straight out. Using the physics that you've definitely been using your whole lives, because you've been watching things fall your whole life, what will the general motion of this rock look like as it goes? Okay, it's going to go forwards and down at the same time, so it'll kind of curve until it goes splat. Kind of like the yellow ball in the picture from a second ago. So, reading the rest of the prompt, rock is thrown perfectly horizontally from the top of the cliff. The two things we're eventually going to solve for are how long is the rock in the air for, we want time, and how far horizontally does it fly from the cliff. What this is asking for is the range, how far horizontally we wound up from start to finish. Notice that didn't ask vertically, because we know vertically how far it's going to be from where we started. It's going to fall 30 feet down. We don't know how far out it's going to go yet. So, I try to lay these out in steps to help get you guys in sort of the pattern set of being able to work these. First, we draw a picture. Be sure to draw the initial velocity vector. That's what this arrow here is. Part B tells us that that initial horizontal launch velocity is 10 meters per second in the x-axis. Sketch that vector and find both the x and y components. What's the y component of a horizontal vector? 0. So we've already done that part. Part C. How much time does it take for this stone to fall from the top of this cliff? This is where the projectile motion part begins. To do these types of questions, the types that you'll see in 19, 20, and 21, we need to look at each axis separately, independent from the other one. Because as long as the object is falling, the horizontal axis has nothing to do with when it will hit the ground. The only thing on Earth that affects the time an object spends in the air is how high you drop it from. So, to look at each axis one at a time, let's look at the y-axis, because that will always be the determinant of how long something is in the air. Y-axis determines hang time every single time. In the y-axis, we know we have an acceleration. We also know we're going to fall 30 feet beneath where we started. So our delta, our y displacement, our delta y for this whole process is going to be negative 30 meters. And we're going to fall 30 feet beneath where we began. What will be, if you throw this rock perfectly horizontally, what is the initial y velocity of the rock? It's 0. We threw it horizontally, it didn't have any initial y velocity, so v initial y-axis is 0. And now we're going to put all those things together to look at the y-axis and determine how much time the rock falls. Because the rock is accelerating, We want to know the rock is accelerating. We know how far it goes. We know its initial velocity, and we want time. Our best bet is going to be tested for formula number 3. I'm going to reframe it a little bit with y's instead of x's. So we displace some distance in the y-axis as we are accelerating. We know that our initial velocity is 0, so this whole term in the middle is just going to go away, and we can solve for t. So always, 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 if you're asked how long something stays in the air, you want to look at the y-axis, and you want to be using this formula. Please do check this yourself. I'm getting about 2.5 seconds of full time. Notice that the negative displacement and the negative acceleration cancel out. We don't have to worry about taking the square root of a negative number. So we have t equals 2.47 seconds. Vertical axis always determines hang time. That's a golden rule you can write down. Y-axis determines hang time. Now that we know the hang time, now we can look at what's going on in the x-axis. Time isn't a vector. You can't have 3 seconds up. So time is the one thing that's going to be shared between both the x and the y here. Because after this many seconds, we hit the ground. We can't fly any further sideways. So this t is the same t that will appear in any formulas we work in the x-axis. T is the one commonality between the two. Because hang time determines how far you're able to go sideways. So vertically, we've fallen 30 meters, we accelerated due to gravity, that whole process took us this long. In that same amount of time, in the horizontal axis, the object has been moving this entire time. It still has its original x velocity. It still has this. And in this time, it's been moving. It's gone some distance forward. Because it's falling, we know automatically it has no x acceleration. We know its initial x velocity, but its x acceleration is 0. That velocity doesn't change. Gravity only works vertically. It will not ever slow something down horizontally or speed it up horizontally. So to begin looking at the x-axis now, we're going to want to use the same formula, but with x's instead of y's. This is easily the best formula to start with in most of these situations. delta x is what we're solving for. We want to know how far it went. So leave that as it is. Initial velocity in the x-axis, that's going to be our 10 meters per second. Time is the time we just solved in the vertical axis. Now, vector is the one thing both axes are going to share. And then 1/2 times x acceleration times time squared. What is the x acceleration? 0. This whole term just goes away. And that should leave us with an x displacement of 24.7 meters. So this is ultimately the range. This is how far you threw the rock, how far it drifted horizontally from where you began. Any questions, comments, concerns, frustrations so far? Yes?
So the time right there is a y component, and then our x component is what exactly is that? What is that value, like the distance?
This?
Yeah.
Yes.
Okay.
This is the horizontal distance that the rock will fly before it hits the ground. So the entire time it's falling down, it's still going to the left, it's still going to the right, and it will go this far by the time it strikes the floor. And time is axis neutral. Time is not really an x component or a y component. It will exist at the same number in both. Although, technically speaking, the y-axis, the distance you fall will determine the time, but that time is still important to the x-axis. How's that feel so far? Okay. I'm going to scroll down to number 20 now. It's a separate question, so don't erase anything you had before. I'm just going to reuse some of the pictures and real estate that I already used, modifying it for a similar question. You don't need to erase anything. Number 20 is very similar with two key differences. One, the launch velocity is changing to 30. Two, we're throwing upwards at an angle now. Oh. My own homework is arguing with itself, apparently. We're keeping the velocity the same. I don't know why I rewrote it as 30 later on. We're keeping the velocity the same, but now it's at an angle. Say that you've been practicing with your pitching arm, and you can just, like, the fastest you can repeatedly chuck out is 10 meters per second, which is very fast. If that's as fast as you can throw, now you're just experimenting with throwing horizontally outwards, with throwing upwards at an angle, and seeing the difference in how far it goes. So this magnitude will remain the same. I know it said 30 here, but it says 10 up here. We're going with that. So erase that 30, replace it with this 10, and I apologize. So in the new picture for this question, because part A still asks you to draw a picture, now that 10 meters per second points this way. And so its trajectory is going to go up a little bit before it hits the ground. Sorry, before it starts going down. So we've gone from just straight out and down to up and down. This is now more visibly part of a parabola. So, a couple things are different now. We still don't know time. We still don't know delta x. We do still know y acceleration. We're still falling. It's still this value because we're still on Earth. From start to finish, like from beginning to end, we're still going to fall 30 meters. We're going to go up first, but we're still going to go all the way down eventually. So our total delta y is still negative 30. But our y velocity initial is no longer 0, because now you've thrown it out and up. So now there's a y piece we need to find. And we're doing this together. I have the answers prepped. We're just going to do a tiny little bit of trig to find Vix and Viy. Sine of 30 equals Viy over 10. I think that should be 5 meters per second. And we will eventually need the x velocity too, so we'll go ahead and find that. Cosine 30 equals Vix over 10. Vix will be 8.66 meters per second in the x-axis. So by throwing it at this angle, we're no longer going as fast in the horizontal axis, but now we are also going up instead. The trade-off is we're not going as fast outwards, but we are now moving upwards at the beginning. Now that upwards trajectory is going to change because we're accelerating the entire time. But at least the initial y velocity is 5 meters per second up. This will change a few things moving forwards. Once you've done this split and you've determined each of the vector pieces, we still need to start by looking at the y-axis to determine hang time, but our formula will change a little bit. Now instead of v initial y times t just going to 0, now it actually remains. So we have a quadratic. Now, I want us to get through this quickly together. We're doing this one together, so I'm going to save us the time and tell us the answer to that quadratic. Right. This will technically give us two answers. That's okay. Make sure I got everything in right. So the two answers the quadratic would give us for time positive 3.04 seconds and negative 2.02 seconds. Now, quadratic will always give us two answers. Because of that squared, there's two different times that would make this work. Which one of them makes physical sense in this situation? 3.04. Because if we start the experiment by throwing the rock, and time is only moving forwards, some amount of time later, it will hit the ground. This number mathematically works, but it exists in a fictional timeline where at some point 2 seconds in the past, someone here threw the rock and it's completing an arc through the earth to end up here. So again, doesn't make any physical sense, only mathematical sense. Because it makes no physical sense, you throw it away. And t equals 3.04 is the part we will keep and continue to use moving forwards. When you have a non-zero initial velocity in the y-axis, you will end up with a quadratic situation like this typically. However, the way we do the horizontal remains unchanged. We plug different numbers in, but the method remains the same. In the horizontal axis, our initial x velocity isn't 10 anymore. It's a little slower in the x because we gave up some horizontal speed to gain some y speed. And our time is now 3.04. But we still have no x acceleration because you can't fall sideways. So that term still goes away. And that will leave us with 8.66 times 3.04. Okay, good. Reality still works. And that multiplication should give us 26.33 meters horizontally. In terms of just the math right now, getting to that number, does anyone have any questions? Okay. Now, talk a little bit about sort of the physics and the reality of this situation as you're writing everything down. Our previous answer, when we threw just horizontally, was 24.7. So by angling it, we have managed to throw it farther. It does raise us some interesting questions, though, because we traveled further even though our x component was smaller. Initially, all 10 meters per second were in the x-axis. Now there's only 8.66 in the x-axis. Because of the way the unit circle works, giving up even a little bit of your x velocity by angling upwards can give you pretty big gains in the y-axis, and that increases your hang time. By throwing it at that angle, now you're in the air longer. So even if you're not moving horizontally as fast, you'll have more time to go outwards at that new reduced speed. So as a result, up to a certain point, you go further. If you ever want to throw as far as possible, there's a magic angle that you always want to throw at, and it's 45 degrees. Because on the unit circle, 45 degrees maximizes the relationship between vertical and horizontal. That's the point where both of them are as big as they can get at the same time, as big as they can get at the same time. And you get the most hang time while still having a decent horizontal velocity to actually get you further out. if your angle measure is above 45 degrees low, like if you're shooting at say 60 degrees, you end up swapping these two numbers. Suddenly you'd only be going 5 in the X and 8.66 in the Y. So you get a lot of hang time. You're just moving really slowly in the X-axis and you don't end up going as far. The extreme case would be if you just threw something straight up. It's not going to go out anywhere, it's just going to come straight back down. Okay. I have been hand waving a lot today and doing a lot of explaining and a lot of just handing you a lot of numbers at once. How do you guys feel so far? Okay. Now that said, I do know that how you guys feel after being presented with this is completely different to what you do with it on your own. So, I am not planning on, we will be revisiting this before the test. The period is ending, and it is not, we will be revisiting this before the test, making sure you guys are comfortable with it before doing much more with it. We are also nearly out of time in the period, so there is a whole other question left on the back. I really want to get most of this homework turned in today so that I can grade it and you can have that graded to study from next week. So, sorry to keep changing you guys. It's not only my first time teaching this particular class, it's just a virus in the world is weird at the moment. Everyone's brains. I'm just monologuing at this point. So, official instructions. Separate the two pages. The first page, the first 20 questions. Oh, nuts. Yeah, no, sorry. The first page, the first 20 questions, all the work for that, turn that in today. Hang on to this one for a little bit longer. We will use this one as further practice and classwork together in the future, but I would like to get this turned in and graded so you have that to be able to study from in the coming weeks. So keep your back page about the basketball player and continue to use your assignment, I guess, over the weekend is look at this, begin working on this in conjunction with looking at these laws. Yes, sorry.
You're fine. That new sheet, that's not due next class period, right?
It is not.
Okay.
So, as clarity, this, the Newton's Law activity, not due next Friday. This is something for the back burner for the next couple of weeks. So, again, official assignment today, turn in 1 through 20 from assignment 7. 1 through 20. Keep the basketball question, work on that as you're studying the coming weeks. We will revisit it. We will revisit it here together as well next Friday. Yes, that's the day. Questions before we break for the weekend? excited by the fact that the blood pressure is already elevated because
Plan is at the moment.